All right, we're going to start taking a look at 18.63a. So I'll write down the question for you. Just grab a pen here. So this is 18.63, no, 18.63a. And it's just a synthesis question. We're starting with anisole. So that's this molecule here, or methoxybenzene, but the common name is anisole. And then we want to make this compound where we still have our methoxy, but we're going to have two substituents. We're going to have a nitro group, and then we're going to have a bromine here. Okay? Now, you need to bring yourself up to some kind of speed that it doesn't take you, you can't take 30 minutes to solve a problem like this. I'm not a big speed guy. I'm not Mr. Fast and Mr. Timing himself or anything like that. But you've got to be able to solve this kind of problem, with in a reasonable amount of time, I would say. Well, the thing that I notice is that we're starting out here with a strong director, or a strong activator, I should say. So here we have a strong activator, and it is an ortho para director. Now we have one substituent in the para position. We have one substituent in the para position. However, if I was to install that first, if I put that, substituent in the para position first, remember that bromine is actually a weak deactivator. So in order to get the bromine in there, I think the best course of action here would be to use fuming sulfuric acid, right? To put a blocking group in, because then we're only going to have the ortho position available. Let me show you what I mean. Okay, so if we take the starting material and we treat it with fuming sulfuric acid, okay, we're going to install the blocking group in the para position, right? Because we've got the methoxy group, which we said is going to preferentially install a substituent in the para position because the ortho positions are a little more hindered. Oops. So we're going to put that sulfonic acid in here. So we got SO3H. That is our blocking group. Now we have an ortho para director here, and we have a meta director here. So now we can install that nitro exactly where we want it if we treat nitric acid and sulfuric acid. So HNO3 and sulfuric acid like that. And that is going to put that nitro group exactly where we want it. Okay, so now we've got our nitro group here, and we have our blocking group, our sulfonic acid. Now we just need to trade the sulfonic acid for a bromine. But the good news is that if we were to get rid of the sulfonic acid, which we would do using dilute sulfuric acid, so we'll put dilute H2SO4. Now we just have orthonitroanisole, this compound here. Okay, now we've got an ortho para director, and we've got a meta director. Well, what's meta to the nitro? The meta position to the nitro is going to be here and here. However, the position that is ortho to the methoxy group is going to be more sterically hindered. And so we're going to get preferential bromination at the para position. So now we can take this guy and we can simply do the bromination chemistry. So we're going to, oops, I wanted to stay with the blue pen here. So we're going to treat it with bromine, Br2, and FeBr3 as our catalyst, like that. And that is probably the best way that I can come up with to do that synthesis and to get a good yield on that synthesis, because we don't want to just make the compound. We want to make the compound and we want to get a good yield of the compound, meaning that we want to choose the best possible route to make the compound. All right. I wanted to take a look at 18.63b next. Just give me 1 second here. Yep. All right, so 18.63b. So moving on to 18.63b. And what you'll notice is that we're starting with the same compound, anisole. Okay, so we're starting with anisole. And now we're going to make a regioisomer of the previous compound, except we're going to put the bromine ortho to the methoxy group. right? Like that. And we're going to put the nitro here. Well, the first thing that I think about with this problem, oh, did I put it in the wrong spot? I did. I'm looking at the other problem, aren't I? I'm looking at the same problem. So we want to have the bromine here, sorry, and the nitro right here. Okay, there we go. Well, the first thing I notice is that if we go backwards, right, if we think of retrosynthesis, so I'll use the green pen to represent my retrosynthesis. If we go backwards and we were to make this compound where we have the methoxy group and the nitro, well, the cool thing about that is that here we have an ortho para director and here we have a meta director. That means that we're going to get preferential electrophilic aromatic substitution at the two positions that are ortho to the methoxy and meta to the nitro. So then the question becomes, well, how do I get from anisole to para-nitroanisole? And the answer is we simply nitrate it, right? Because this is already an ortho para director and the methoxy group is an activator. So what we're going to do is we're going to treat this with nitric acid and sulfuric acid, and you should know that that forms the nitronium ion, right? And you should be able to draw the nitronium ion, and you should be able to draw the mechanism of nitration. Here we go. And you're going to end up nitrating in the para position like this. So we have our nitro group here. And then all we have to do is one more step, right? All we have to do is brominate it. So we're going to treat it with bromine and iron 3 bromide, and we're done. Just like that. So the first one, we had to use the blocking group and remove that blocking group, of course. But in the second one, we can just treat it as a two-step synthesis because the nitration is going to occur where we want it to. And then the bromination is going to occur exactly where we want it to. All right. Let's take a look at another one. I wanted to try 18.63C. So this is 18.63C. We're starting it with an isopropyl group, which you're going to find is used an awful lot in this chapter. So we have isopropyl benzene, and we want to convert it to a benzoic acid derivative. So we're going to put our carboxyl group up here. So that's our carboxylic acid. And then we want to have a nitro group right there. Can anybody make a suggestion where you might want to start with this one? Sorry, Skylar, I got to open up my chat here. I can't see. Yeah, somebody says a blocking group. I agree. I think we would want to start with a blocking group here, right? Because if we want to put in this nitro group, okay, we do have an ortho para director here. However, since this isopropyl group has free rotation around this sigma bond, if we were to just treat this with nitric acid, we would just get nitration here, right? We would get very little nitration occurring in the ortho position. And so, like Skylar says, I think the best thing to do would be to treat this with fuming sulfuric acid, install a blocking group. So let's do that. There we go. We've got our blocking group like this. And now the sulfonic acid is a meta director. And here we have an ortho para director. So you can see that we're going to be directing the nitration at this position. So like Skylar says, we have blocking group, then we have nitration. So what are the conditions for nitration? We use nitric acid and sulfuric acid together. We're going to nitrate the ring. So we're going to install the nitro group here. Go. Now we want to remove the blocking group. So we're going to use dilute sulfuric acid. Kind of running out of space here. There we go. In the last step, somebody said oxidation, and I agree because if we do an oxidation at the benzylic position and there is a proton here, right, all we have to do is a benzylic oxidation. Now there's a couple options. We can do the benzylic oxidation in acid using chromic acid, or we could do it in base. Now, I don't know which one they choose in the textbook, but you could choose KMnO4 and sodium hydroxide and heat, followed by dilute acid. That works. Or you could just choose chromic acid. So I'll just write that. So I'm going to put sodium dichromate, sulfuric acid, and water, like that. And again, here in this step, you could use potassium permanganate, sodium hydroxide, and heat. And then in the second step, you could just treat with acid. Either way is totally acceptable. All right. So you can see that these questions, here we have what? 1, 2, 3, 4 steps, but it's a matter of knowing the reactions well in order to solve these problems. Let's take a look at 18.63D. So now we're moving on to 18.63D. We're going to start it with that isopropyl benzene, which I've told you before is called cumene. And then we're going to take that and we're going to make another carboxylic acid derivative here. And now we've got the nitro meta to the carboxyl group. Well, what's interesting about this is now we have the nitro group meta to the carboxyl group, and a carboxyl group, rather. The carboxyl group is a meta director. It's a moderate deactivator, but it's a meta director. And so if we were to convert this to the carboxyl group first, then we can have a meta director and we can install the nitro. So could anybody suggest what I would want to do here first? And it's not a trick. Mr. Dion is not into the trick questions. I just don't like them. Sorry, I can't see my chat. Where is it, Glenn? Yeah, exactly. Somebody's saying oxidation. I agree. I think that's probably the best place to start here. Exactly. We'd want to start by doing a benzylic oxidation, right? And then after we do the benzylic oxidation, we'll have our carboxyl group in place. So let's start by doing that. Again, remember, we have a benzylic proton here, which is required for benzylic oxidation. So we're going to take it. Let's choose sodium dichromate again. It just seems like it's faster to write down to me. Sulfuric acid and water. And then we'll make benzoic acid. So let's do that. We have benzoic acid here. Again, the carboxyl group is a moderate deactivator, but it's a meta director. So it's going to direct to this position. So that means all we have to do is treat this with the conditions for nitration, which are nitric acid and sulfuric acid mixed together, which makes the nitronium. We have an electrophilic aromatic substitution, and there you have it. All right. Well, let's turn our attention to 18.67. I'm just trying to find it here in my notes. So 18.67. Just give me a second here. These ones are a little more complicated because we have multiple substituents. So let's start with 18.67A. I think it's a good place to start. So this is 18.67, and we're going to start with A. So starting with benzene and anything else of your choice, design a synthesis. So that means we're going to start with benzene. And somehow we're going to end up with this molecule. So we got this guy. We've got a methoxy group here. We've got a bromine here, and we've got a bromine here. What else? We've got a nitro here. Does anybody notice anything? Well, I guess I should ask it another way. How many ways do we know how to install a methoxy on an aromatic ring? Can anybody tell me what we might do to put a methoxy group on an aromatic ring? It seems like an interesting thing to do. And it's not a trick or anything. How many ways do we have to put a methoxy group on an aromatic ring? The only way that I can think of is an SNAR reaction. right? It's really the only way that we have to put an oxygen on an aromatic ring anyway, right? The only way that we know how to make phenol, right? To make I should say a phenol, really, is to start it with the chloride and have a nitro group here. So what am I saying? What I'm saying is that if we could just make this compound, I'll use my retrosynthetic analysis here. If we could have this compound, okay, well, then we'd have a meta-director, and then we'd have an ortho-para-director. All we'd have to do is 2 successive brominations to put those in. So then the question becomes, how do I get from here to here? Well, here's what I would do. I would start by making chlorobenzene. So I'd start by taking this, and I'd treat it with, chlorine and iron 3 chloride. So let's do Cl2 and FeCl3, like that. And we would end up with chlorobenzene. It's this molecule here. Then if I want to do an SNAR, I need to install a nitro group. So the chlorine is a weak deactivator, but it's an ortho-para-director. And I'm going to get preferential nitration down here at the para position. So I'll treat that with nitric acid and sulfuric acid. And I'll make para-nitro-chlorobenzene. This right here. Now I can do an SNAR. Now we only looked at SNARs, I think, last class, correct me if I'm wrong, but we only looked at them where we used hydroxide as our nucleophile, right? And we drew, I guess I need to put some bonds in here, don't I? We drew the curved arrows for the SNAR reaction methoxide, right? Why couldn't we use OCH3? So why couldn't we use sodium methoxide and have that as our nucleophile? There's no reason why we couldn't do that. So we'll use sodium methoxide and heat, and that's going to do our SNAR reaction. And then we would have the methoxy group in the right place. So we have our methoxy, and then we have our nitro. So the methoxy is going to be a strong activator. It's an ortho-para-director. This is a meta-director. So now our bromination is only going to occur at these positions. So, I mean, you could put 2 brominations in a row if you want. I think the way I would write it would just be to use excess bromine. So we'll just put excess, tons of bromine and tons of iron 3 bromide. And we're going to get all kinds of, or we're going to get both of these bromines installed there. Give me a thumbs up if you follow me on that. Or does everybody follow me on that, guy? I don't think that's a trivial question. I don't think that's an easy question by any stretch of the means, but it's a question that's, definitely doable considering our skill set that we have at this point. Cha? No? Okay. Well, if you're unsure, if you have a question, don't be afraid to stop me at any point. And sorry, I just want to double check. Yeah, I just want to double check to see what question. I had another one. I know there was one I really wanted to do here. Oh, let's try 18.67b. I think this one's a little quicker. I don't think it's easy. If it was easy, anybody off the street could do it, right? So 18.67b, we're going to start with benzene. And the compound they want us to make has 2 carboxyl groups on it. So we have a carboxyl group here. So that's just a carboxylic acid. We have one there, and then we have one here, like that. All right. Now, I would say there might be a couple of different ways that you could solve this one. But what I'm thinking is, if we have 2 meta-directors here, right? The carboxyl group is a moderate deactivator, and it's a meta-director. So we have a meta-director here and here. So that means in terms of retrosynthesis, we want to have, this, the 2 carboxyl groups, and then all we have to do is the nitration in the last step. But now that I'm thinking about it, I think there's an even better way to do that, because these 2 groups are deactivating. So if instead of deactivating groups, what if we had 2 activating groups, right? What if we had, I didn't mean to do that. What if we had two methyl groups, like a methyl group here and a methyl group here? Well, those are both going to be activators, and that would give us a higher yield of nitration, right? That would definitely give us a higher yield of nitration. But something else to think about is if we want to put two groups para, two R groups para, well, if I only have a methyl group here, then remember that this is an exception, and I would mostly get R groups installed here. So what I'm going to need to do is put something that's bigger and bulkier here, like an isopropyl, for example. It can't be a tert-butyl. I can't do that because I have to have at least one benzylic proton here. So how would we make this compound? Well, we would start by doing the Friedel-Crafts alkylation. So we would take isopropyl chloride and aluminum chloride, and then we would install the isopropyl group first, after which we would install the methyl group, right? Because this is a weak activator, but it is an ortho-para director. But since there's free rotation around this bond, we would get preferential alkylation here if we were to treat this with methyl chloride, let's say, and aluminum chloride. Then we're going to have this guy where we have our isopropyl group and we have our methyl group here. Now, these are both weak activators, which would be better than having the two carboxyl groups, which are moderate deactivators. So now let's do our nitration. That's, I think, would be the best thing to do next. So we'll take that and we'll treat it with nitric acid, sulfuric acid, and we're going to end up with the nitro. And the nitro group is going to be in this position. So it's going to end up next to the smaller group, like that. And then the last thing that we're going to do, again, since we have that benzylic proton, all we have to do is do the benzylic oxidation. So let's do it in basic conditions. First, we'll treat it with potassium permanganate, sodium hydroxide, and we'll heat it. And then in the second step, we're going to treat it with dilute acid. And that will give us our desired product. Remember, it would be, I mean, it will be in this orientation, right? You'd have your carboxyl group up here, your nitro group here, and your other carboxyl group here. But this is the exact same thing as this, isn't it? Okay, there we go. That's another good problem. Let's see here. I had some other ones. Let's try 18.67C. So just moving down the line here. 18.67C. It's good to imagine yourself on a test or exam, maybe. 18.67C. So we're always given benzene as a starting material, and we're making another tetra substituted compound. Here we get this big old tert-butyl group on the top. There's only one way to install that. That would be Friedel-Crafts alkylation. So we're going to have to use that at some point. Then we've got a bromine here. We've got a chlorine here. And then we've got a nitro group here. Well, I know that in terms of my retrosynthesis, I've got a meta director here and an ortho-para director here, but I've got to have both of these installed first in order to put the bromine and the chlorine in, right? If I didn't have the nitro group in and I tried to do a bromination or a chlorination, it would all go in this position. So that won't work. So that means I'm going to have somehow, I'm going to have to make this compound, right? And I'm going to start by installing the tert-butyl group because it's an ortho-para director. And since I have free rotation around this bond, I'm going to get preferential nitration in this position. So now I think the question becomes a lot easier, right? We're going to treat this with tert-butyl chloride and aluminum chloride. This is just a Friedel-Crafts alkylation. Okay, we went over this last class on Friday, I believe. There we go. And that gives us tert-butyl benzene, this compound. Okay, now we have an ortho-para director, and we're going to get almost exclusive electrophilic aromatic substitution at the para position since this is so big and sterically hindered. So we're going to treat this with nitric acid and sulfuric acid simultaneously in order to affect the nitration. So let's draw the nitro group in here, and let's put our tert-butyl group like this. Now, again, we've got everything installed. We've got a meta director here, and we've got an ortho-para director here, but the para position is blocked. That means that everything is going to be directed to these two positions. So first, we'll do the chlorination. You could do either one. You could put the bromine in first. It doesn't matter. First, I'll put the chlorine in. So I'll use chlorine, and I'm going to use aluminum chloride just for fun. That's going to put my chlorine group in, my chlorine atom, I should say, right here. There we go. There's my nitro. And then to get to the product, we're going to use bromine. And I'll use iron 3 bromide, just like that. There you go. So how many steps is that? It's 1, 2, 3, 4 steps total to make this compound. No blocking groups required, which is kind of nice. So that was C. With that in mind, I had done a bunch of them here. Let's try something that's a little spicier, maybe. Let's try G. So this is 18.67 G. I want to scroll down, make sure I wrote down the question correctly. Yeah, let's do G and H. So 18.67 G. Here we go. So let's see here. I've got benzene, and I want to make this molecule where I've got an isopropyl group at the top. The only way I can put that in is with Friedel-Crafts Alkylation. I've got a chlorine, I've got a nitro group, and I've got this acyl group here. This is a good one to solve using retrosynthesis. I mean, could anybody tell me which one of these groups you would install last? Would it be the isopropyl, the nitro, the acyl group, or the chlorine? Which one would you install last? Yeah, exactly. I would install the chloro last too, right? So just in terms of my retrosynthesis, you know, oops, I didn't mean to do that. I want to make this molecule. I want to have the isopropyl, I want to have the nitro, and I want to have the acyl group installed, right? Because then you've got an ortho-para director, which is going to direct to this position. You've got a meta director here, which is going to direct to this position. And you've got a meta director here, which will also direct to this position. So that would be the logical last thing to do. Just in terms of our retrosynthesis, I think the second to last thing that you would want to do, and let's do 2 retrosynthetic steps, would be the nitro, right? Because if you have the isopropyl installed, and if you have the acyl group installed like that, right? This is an ortho-para director. The para position is blocked, and this is a meta director. So those are going to direct to this position, right? So, you know, we can just keep doing retrosynthesis here. And if this is a meta director and this is an ortho-para director, well, then logically going backwards, one more step, we would want to have isopropyl benzene, right, as our starting material. So then, you know, how do we get from here, then to here, then to here, then to here? Well, let's start over. So let's start over. So this is still 18.67. And still, this is question G. Okay, so we're going to make the isopropyl benzene first. How do we do that? We take benzene, we treat it with isopropyl chloride, aluminum chloride, our Lewis acid. We do the Friedel-Crafts alkylation because we're adding an alkyl group. Now we've got the isopropyl group in place. Next thing we're going to do is install the acyl group. So this requires a Friedel-Crafts acylation. So we need the carbonyl, we need a chlorine. We have 1, 2, 3 carbons, right? We have 1, 2, 3, right? There's 1, 2, 3 carbons in the product on the acyl chain. So there we go. So this is called propionyl chloride. It's neither here nor there, but that's going to go at the para position, right? Preferentially. So now we've got our acyl group. So let's draw that. It's our isopropyl group. Here's our acyl group. Next, again, we have our ortho-para director, para positions blocked. We have the meta director. So we can put in our nitro. And the reason we want to do that first is because we'd end up with a higher yield because the nitro is also a meta director. So we're going to put this in, sulfuric acid, nitric acid. So we'll install our nitro group in this position. And we've got our acyl group here. And then the last thing that we need to do is chlorination. So we'll treat it with chlorine and aluminum chloride, like that. And that will give us our final product where we have our isopropyl group, our nitro group, our acyl group, and we'll also have our chlorine, like that. There you go. So you have to take the steps into consideration when you're doing these kind of problems. You have to be very careful about which step you take at which time. Okay, I want to try another one from 18.67. And this is H, 18.67H, which I think is a real humdinger. 18.67H. You want to start it with benzene, and then you want to make this bicyclic compound where you have your aromatic ring, but fused to the aromatic ring, you have a 6-membered ring. You have methyl groups here, then you have a bromine here, and then you have a nitro group here. Well, what I think we need to do first is to make the bicyclic structure because of those two geminal dimethyl groups. Remember, geminal is twins, right? Gemini. Because of this guy and this guy, those are so sterically hindered, right? And these are both alkyl groups, which are ortho-para directors. But if I'm talking about this group, well, then I have, it's going to direct ortho here and para here. And if I'm talking about this guy, it's going to direct ortho here and para here. So no matter what, I'm going to end up, putting the group at the least hindered position because these methyl groups are just so dang big, right? So I could do the bromination first. I would probably do the bromination first since the nitro is ortho to the bromine and the bromine is ortho directing. Right, no matter what, these positions that I'm writing the yellow protons in, those are sterically hindered because of these big, methyl groups over here. So then the question becomes, how do I make this guy here, right? How do I make this? Well, this is one of those questions that I asked you to look at, so I'm not going to talk about it all night, but you can see how in terms of a Friedel-Crafts, right, the only way we have to make a carbon-carbon bond to do an alkyl group, we just need to break these two bonds. Then what would we have? We'd have gem dimethyl, 1, 2, there we go, and we'd have another gem dimethyl. So we need to have a chlorine here and a chlorine here, right? And we're not going to get any rearrangement. So we're going to start with our aromatic ring. We're going to treat it with 1, 2, 3, 4, like this. Then we have our gem dimethyls like this and aluminum chloride, and that's going to give us our bicyclic compound. Let me draw my double bonds properly, like that. So that'll give us this compound. Next, we're going to install the bromine. So we do that with bromine. I'll choose aluminum bromide this time, doesn't matter. And that's going to put the bromine where we want it. And then since it's an ortho para director, we can just do the nitration. So I've got my bromine here, right? And that's going to direct to the two ortho positions in the para. The para is blocked, and then this one is too sterically hindered. So it's going to direct to this position when I do the nitration. And thus I treat it with nitric acid and sulfuric acid, just like that. All right. Let's take a look at 18.75 now. So if you scroll down in the practice problems into the integrated problems, there's a couple here that I just wanted to take a gander at quickly. 18.75a, I think, is a good one. So this is, where's my pen? 18.75A. And it says here, starting with benzene and any other reagents of your choice, design a synthesis for each of the following compounds. Each compound has a bromine and one other substituent that we did not learn how to install. In each case, you will need to choose one of the substituents that we learned in this chapter and then modify that substituent using reactions from previous chapters. Be careful to consider the order of events. Okay. So I think retrosynthesis is going to be our friend here because we want to start with benzene. Then somehow we want to make this para-substituted compound, no, sorry, meta-substituted, where I have a bromine here and I have a tertiary alcohol over here. Well, we never looked at anything that involved installing a tertiary alcohol on an aromatic ring. But in terms of retrosynthesis, if I could make this compound, where I have a bromine here, and I have a methyl ketone here, which we could make from acylation, all I would have to do is a Grignard reaction, right? Going this way. Okay, I would just treat that with methyl magnesium bromide as my nucleophile, and then the acid in the second step to make the tertiary alcohol. So then the question becomes, well, how do I get from here to here? Well, the acyl group is a meta-director, and the bromine is an ortho-para director, so I want to install the acyl group first. Let's put in our acyl group. So we're going to use acetyl chloride, aluminum chloride, and that's going to install our acetyl group. So let's put that in. Okay, it's a meta-director. So now we've got a beautiful meta-director. It's a moderate deactivator. There's no reason why we can't do a bromination though. So let's take that and we'll treat it with bromine. And I'll choose aluminum bromide this time. Doesn't matter. You could have chosen iron 3 bromide. That's totally fine. And now we've got this meta-bromo-acetophenone. And then in order to make the tertiary alcohol, in the first step, I'm going to treat this with methyl magnesium bromide. I'm writing it out with the full charges here because remember, the first step is going to be a nucleophilic attack like this. And then in the second step, you're going to treat that with water to do the protonation. So this one involves the Grignard reaction, right? Grignard chemistry. The next one, I kind of wanted to leave the first one up. I'm running out of space here. Anyhow, let me write down the second one here. So this is 18.75. Nah, I'll just have to take more space. So this is 18.75. B. Okay, we want to take benzene, and somehow we want to make this compound where we've got a bromine here, and then para to it, we've got this group here. Well, there's a couple of ways I could think about doing this. You know, I'm just thinking about, there's a way that I can think of that we haven't learned yet, so that doesn't really help us, and it doesn't. Using what's called the Wittig reaction, and that's something we'll see in chapter 9, but that does, chapter 19 rather, but that doesn't help us today, does it? So I think the easiest way to do this would be if we could make that tertiary alcohol, right, like we did in the first one, if we could make, you know, this compound, except with the bromine in the para position. Well, going back this way, all we have to do is heat sulfuric acid and heat, and that will make, you know, the alkene, which is completely conjugated with the ring. So it's going to make it really easily. So then the question becomes, well, how do I get from benzene to this compound? You know, how do I get from benzene to there? Well, I mean, the bromine is an ortho-para director. And remember that we're going to make this from the acetyl group. So let me just draw that out quickly. I'd want my bromine here and I want my acetyl group here, right? And then I'm just going to do Grignard chemistry here. So since the bromine is ortho-para directing, why don't I install that first since this is a meta-director? So we'll start with our benzene, and we'll put bromine on first. So we've got bromine and aluminum bromide. What's going on there? Like losing power or something. So now I've got my bromine in this position. I do the Friedel-Crafts acylation with acetyl chloride, and aluminum chloride is my Lewis acid. Now I've got my acetyl group, and I've got my bromine. Now I can do my Grignard chemistry. I'm going to run out of space here, aren't I? So I'll put step 1 is methyl magnesium bromide. Step 2 is water. And I'm going to end up with this compound. So I've got my tertiary alcohol. There we go. I think I'm not going to run out of space now. And then I'll just treat it with H3O plus and heat in the end. And there you have it. And I mean, I know the book probably says concentrated sulfuric acid. That's fine too. Okay, either way, just dehydrating it, right? You're losing water is what you're doing. And there you have it, folks. That's some good practice problems. They are not easy. I don't think they are. I warned you from the get-go. It's a challenging chapter, chapter 18. But this is the kind of level that you want to bring yourself up to for the quiz this week.